Dr. Rico here. This is a lecture from my course, System Dynamics. The syllabus link is in the description. All right, we're going to do an example today with state space response techniques. And this example is going to have two vibration modes associated with it. So we're going to dig into that. Both an undamped case where each of the vibration modes is undamped, and we're going to do a case where we add in a little damping, and we're going to see what happens to those two vibration modes when we add a little damping in. So we're going to do both of those cases in the following example. We're going to use MATLAB as our computation tool to help us out, and we're going to use analytic techniques. So let's take a look. So consider the system of figure vibe.1, which is shown up here, in which a velocity source Vs is applied to a spring K1, which connects to a mass M1, which in turn is connected via springs K2 and damper B2 to mass 2. All right. A state space model, A matrix, for this system is given below. So we could go through the process of drawing a linear graph and deriving from that linear graph a state space model. So go back and take a look at those techniques if you are a little fuzzy on them. But this is the A matrix that we would get if we went through that analysis. So we see that it's a 4x4 matrix, which means that we have a fourth order system, right? And that there are 4 state variables. I actually didn't explicitly say which 4 state variables we have. So it's a little bit ambiguous. You could probably figure it out if you were to look a little bit closer at these. But it actually doesn't matter in terms of the vibration modes. So we're going to ignore what the physical quantities are of those state variables for this example. All right, so the parameters in here are the mass M1, which is given as 0.1. We don't put units here, but as usual, we're probably working in kilograms here. And mass 2 is much heavier. So mass 1 is like around 10% the mass of mass 2. Okay, so mass 2 is the heavy one. Mass 1 is just the little guy hanging out here. All right, but all of the transmission of the input goes through that mass 1, so it's important. Great. K1 and K2 are about the same, 8 and 9 Newton per meter, right? Great. So those are the parameters that we have. We haven't specified B. So this is MATLAB code specifying M1, M2, K1, and K2. We haven't specified B. And B shows up throughout the A matrix. So of course it's going to affect the dynamics of the system. But since we're going to try out 2 different values of B, we'll leave it undefined for now. 2 different values are given. 0 is 1, so we're going to have no damping. If you look back at the system, we see that we only have one element that is a dissipative element. So the other elements are not going to dissipate energy from the system. And that means that we're going to have energy stored in the spring and the mass, and this spring and this mass. And the energy might move around, slosh around in the system, but it's not going to dissipate when B2 is 0, when there's no damping there. Okay. But when B2 is non-zero, there is an outlet for energy, and so energy will be converted into heat with that damper. So that damping of 20 Newton second per meters is going to be what we explore in the second part of the problem. So let's look at the free response of the system. We could look at the forced response, but for now we're sort of taking it easy in our analysis, and we're just going to look at the free response, which is quite easy to solve for analytically, of course, using the methods of this state space response chapter. All right. So the first case, without damping. All right. Without damping, we expect the system to be marginally stable and have two pairs of second-order undamped subsystems with their own unique natural frequencies. So remember, higher order systems above second order, you can think of them as being comprised of subsystems that are first and second order. Since we have no damping and we have a fourth order system, we expect there to be two marginally stable poles or roots of the characteristic equation, or eigenvalues, right? As we've learned to identify. So we set the damping coefficient to 0 for the first part of this problem, and we define the A matrix. And in MATLAB, we'll just plug in those values. It'll substitute in numerical values for each of these and compute the A matrix, which is given here. Great. So, to explore the modes of vibration, consider the eigendecomposition of A. We know that in MATLAB, we can simply use the eig function, and it will return two different variable definitions, which will be L, the eigenvalue matrix, and M, the modal or eigenvector matrix. So we get those two matrices back. Let's go ahead and print out the eigenvalues. And what we see here is that there are 0 real parts on all of these, and the imaginary parts show up as complex conjugate pairs. Okay, so that is the hallmark, of course, of marginal stability. And what we can see here is that there are two different complex conjugate pairs. Okay, so this is a pair, and this is a pair. So just from looking at the eigenvalues of the A matrix, we know quite a bit about the system. We know its stability situation. We know since it's marginally stable, if we give it any initial condition, most likely, there are some edge cases here, but if we give it an initial condition that excites any of these marginally stable modes, then we will see an oscillatory response for all of time, and there will be no damping out of that response. So that's what we see happening here. We also know that there are two different natural frequencies associated with this system because we have two different pairs of complex conjugate eigenvalues. So let's take a look. So when we have this case of two different complex conjugate pairs of eigenvalues, we can say that there are two different modes of vibration. Okay. And similarly, we could say that there are two second-order systems comprising this fourth-order system. When we consider what the natural frequency and damping ratio is for each pair, we're considering the natural frequencies associated with each mode of vibration. So this is really getting you a foot into, or maybe a toe into, the field of vibration analysis, which is built upon the field of system dynamics, which we're already swimming in, if you will. For a second order system, so you can go back and look at the trans.secondo lecture, the roots of the characteristic equation, which are equal to the eigenvalues corresponding to the second order pair, are given in terms of the natural frequency omega n and damping ratio zeta. So that means we have a natural frequency and a damping ratio for each of these modes. But for now, let's see what happens with just one of them. So for each of the modes, we have this situation. the eigenvalues show up as a pair of poles defined in terms of omega n and zeta as negative omega n zeta plus or minus omega n square root. So the roots of the second order system's characteristic equation, or the pair of eigenvalues that show up that describe a second order system, subsystem in this case, are in this form. And from this form, we can identify the natural frequency and damping ratio for a given set of eigenvalues. So the imaginary part is non-zero only when zeta is in the range 0 to 1. If you look here, zeta squared minus 1 is going to be negative when zeta is between 0 and 1, which leads to a square root of negative 1, which is of course the imaginary number. So when the system is underdamped or undamped, we get the case that we could rewrite this negative omega n zeta plus or minus j, the imaginary number, which we've now factored out, omega n square root of 1 minus zeta squared. So as long as zeta is between 0 and 1, including 0, not including 1, we have this imaginary j showing up here. Great. This, taken with the fact that the eigenvalues from the L matrix we've defined have 0 real parts. Okay, so if we back up here for just a moment, we remember all the real parts of the eigenvalues were 0 in our case. Implies that either the natural frequency or the damping ratio associated with each of these modes is 0. The real part is comprised of the product of natural frequency and damping ratio. So if the real part's 0, one of those at least has to be 0. However, if the natural frequency is 0, the eigenvalues would all be 0. That being the case because both terms have an omega n in there as a multiplicative factor, and it would create a completely 0 eigenvalue. And they're not. In our case, we have a non-zero imaginary part. So it can't be the case that omega n is 0. Therefore, zeta is 0 for both pairs of eigenvalues. This leaves us with the eigenvalues plus or minus j omega n1 and plus or minus j omega n2. So if zeta is 0, coming back up here, this part is 0, and this part is the square root of 1 minus 0, which is just the square root of 1, which is just 1, plus or minus j omega n, and then we have one of those for each pair of our eigenvalues, of our complex conjugate eigenvalues. So we have this situation for one pair, and then we name it with a 2 subscript in this other case. So we can easily identify the natural frequencies, omega n1 and omega n2, associated with each mode as follows. We just take the imaginary part of the 1, 1 eigenvalue. So this is a matrix, right? It's a 4 by 4 matrix of eigenvalues, L is. And this is the 1, 1 component. This is the 2, 2 component. This is the 3, 3 component. This is the 4, 4 component. And those correspond to the first eigenvalue, the second eigenvalue, the third eigenvalue, and the fourth eigenvalue. So we take the 1, 1, which corresponds to the first eigenvalue, and we take the imaginary part here. The imaginary part is going to give us going back to where we printed this out, it's going to give us 9.3818. And we're going to do the same thing with the 3,3 eigenvalue to pick out that imaginary part. Okay? The natural frequencies are just those two values. Okay? So if we see here, the imaginary part of this and the imaginary part of that are the two natural frequencies. So we can identify them by just selecting them out and printing them. And sure enough, when we print them, we get 9.38 and 2.73. So we have succeeded in identifying the two natural frequencies corresponding to the two modes of vibration for this problem. All right. Now let's look at the free response. Let's compute the free response to some initial conditions. The free state response is given by x of t equals the state transition matrix, capital Phi of t, times the initial state vector. So we can find this from the state transition matrix Phi, which is known from lecture state space response diagonalizing basis, ssresp.diag, to be the modal matrix of eigenvectors, which we already computed, times the state transition matrix Phi prime. Okay, so in the primed basis, as we described it before, meaning the basis that is diagonalized via a specific basis transformation of the original state space, times M inverse. Okay? So this is the computation for Phi, the state transition matrix that we need. And once we have Phi, this free response is given, essentially. An initial condition is given. We multiply that by the state transition matrix, and we are already at our free response. So we need to construct Phi prime symbolically. Remember that the state transition matrix in the primed basis is simply equal to the matrix exponential of the eigenvalue matrix, which we usually use symbolically capital lambda, but here we are using L, we could say, for lambda, because we've defined that matrix already from the eig function in MATLAB, times t. This is diagonal, and remember, with a diagonal matrix in the matrix exponential, it's very easy to compute that the diagonal state transition matrix then is e to the lambda 1t, e to the lambda 2t, e to the lambda 3t, e to the lambda e to the lambda 4t, and zeros elsewhere. So this is why we go through this whole show. We do all this transforming of basis and all that so that we can easily compute the state transition matrix in the primed basis or in the diagonal basis. And this then becomes our phi prime. And then all we need to do is transform it back using this expression up here, and we're good to go. So we'll do that symbolically first. So declare t to be symbolic, define an anonymous function, phi p for phi prime, which is a function of time. This diag of x of L t is a construction that essentially creates this automatically without assuming a certain dimension to L. I wrote it like this so that we can reuse this code for other dimensions of A matrix, other dimensions of eigenvalue matrix L. So let's print it out. And it's a little bit hard to read, but we see that just as we expect, we have e to the lambda t on the diagonal going down and zeros everywhere else. Okay, great. So we've got our phi prime. Now we apply that transformation. We can do it symbolically here as well. M inverse, let's compute it once outside of the definition of phi so that we wouldn't be calling it inverse every time. MATLAB is very efficient at doing this, but it's good practice to pre-compute an inverse like this. And we do m phi prime, m inverse to get phi. So our symbolic solution is to multiply the initial conditions by this matrix. Okay? We declare an initial condition. We could have given it anything. We just are curious to see what happens. So we'll just say that the first state variable is 1 and every other state variable is 0 at the initial condition. We take the product and we just see what comes out. So there are going to be 4 values. The state vector is of length 4, x1, x2, x3, and x4. And these expressions include these imaginary exponentials, which show up in pairs, right? So you might say the state vector is real, so how are we going to get these complex values in the state vector? That doesn't make a lot of sense. Well, notice that these are imaginary numbers showing up in exponentials that have pairs. And those are, of course, just sinusoids. So we could symbolically explore how to express this, even using MATLAB's symbolic toolbox, in terms of cosines and sines, which I would encourage you to do. But imaginary exponentials or complex exponentials, despite the fact that they are sort of strange looking to us, are completely valid real functions, okay? So we don't necessarily need to be scared of them. We could treat these as the answer. In some ways, they're less challenging to look at than the expanded trigonometric forms. So if you're comfortable with them like this, you don't need to worry about transforming them into sinusoids, which using Euler's formula, it's just a little tedious sometimes, but isn't too bad. We can always do that if we like. So let's plot a free response. Let's make the symbolic solution into something we can evaluate numerically and plot first, because in order to do plots, we have to evaluate things at given moments of time. So a nice way to do that is to take a symbolic function. We're going to turn this x into a numerically evaluable function. MATLAB does not really like evaluating symbolic functions into numeric expressions. So it has this nice built-in function called MATLAB function, aptly named, that takes a symbolic expression and returns a numerically evaluable function. All right, so in this case, there's only one variable in it that's symbolic, so it knows that it's now a function of whatever that variable is, which is t, time for us. So xfun is the numerically evaluable function for us. Now, let's set up our time array for the plot. We want to evaluate this at specific moments in time. So we'll go from 0 to 5 seconds. We'll take 300 points. There are ways to decide how long you should do your plots for. And those mostly come down to how long does it take your system to come to a steady state? What are the frequencies that are associated with your system? Do you have any really high frequencies? You're going to need more points in there. Do you decay really quickly to a steady state? you're going to want to simulate for a shorter amount of time. Do you decay very slowly, longer amount of time? So this is kind of a many-faceted decision. But one way is to guess and check, try out a couple of reasonable values and see what comes out. It's a little dangerous to do that without some forethought. For us, we especially need to worry about these natural frequencies, fairly pedestrian natural frequencies for us. So they're 3 and 9 radians per second. Nothing that we won't capture in 5 seconds with 300 points. So that's why we chose that. Plot the state responses through time. The output is shown in this figure. So we'll just use, open up a figure, we'll use the plot function. And this is a bit of a cheat here. So I'm evaluating this function at all the different time values. However, given the complex exponential form of this, there is MATLAB doesn't by default compute it as real, it computes it as complex. And due to the numerical nature of this, there are going to be tiny imaginary parts left over. Very, very small. It's good. So MATLAB will actually give you a warning if you don't ask it for the real part. So what you should do is first make sure that the real part of these is very, very small. And I checked to make sure that I didn't make a mistake. You should check, if you're getting that warning, that your imaginary parts are in fact very, very small before using this real function. So let's take a look. Okay, so this is our state free response. We have these 4 mysterious state variables that I never explained what they were, but you can easily plot them: x1, x2, x3, x4, no problem. And we see that x1 starts off at 1, the initial condition, and the others start off at 0, their initial conditions, and they happily oscillate along, apparently never damping down, which is actually what we expect, right? We just expect to see these oscillations occur. Notice that we have a sum of sinusoids in x3 and x4 that are pretty significant in their mixing. So that you see it in x1 and x2 as well, because it's not just a simple sinusoid. Because notice, for instance, if you take a look at the orange one, the peak here and the peak here and the peak here, they're different, right? Those peaks are different heights, and so a pure sinusoid wouldn't have different height peaks. The other pair, x3 and x4, it's more clear that this is not just a sinusoid, right? That there's something else going on. It's the sum of a couple sinusoids at different frequencies. So we're seeing the 2 different modes of vibration that are being summed. I said they're clearly mixing. That's a really fraught word in the context of sinusoids. Probably wasn't the right word to use there, because mixing typically means the product of sinusoids instead of the sum, but they're mixing in the sense of a sum here. Okay, so we've got the state response analytically, plotted it up. Everything's good. Looks pretty. We're pretty excited about it. Now, and it wasn't too hard either, and we actually used MATLAB to do all of the calculation for us, so we didn't have to do anything by hand. It was pretty easy. Now, we would like to know what happens if we add a little damping in, right? We started out this problem by zeroing out the damping coefficient of the one damper in the system. So we got these oscillations that just can continue forever. What we're curious to see is what happens now if we increase that damping from 0 to some finite value. 20 was the numerical value that we stated. So let's try that out. With a little damping, we change B. Again, that's the damping coefficient, not the damping ratio, not the damping, or not the B matrix of the state space variety, just the damping coefficient. So we recompute A. This isn't the most elegant way of doing a programming problem, but it's very explicit so you can see what's going on. So that's the way we're going to do it. We'll recompute the A matrix. It's nice to look at these A matrices, slow down a little bit and look at them. In the first one, we had a bunch of zeros along the diagonal and a bunch of symmetry off the diagonal. In this one, we have some zeros along the diagonal, and we have this negative 200, negative 18 showing up on the diagonal now. So we don't quite have that. We don't quite have the symmetry that we had before either. So, this one's clearly different, and it's kind of interesting to see how it affects what the A matrix looks like. Let's compute the eigenvalues again. So we're essentially going to go through the same process, just noticing the differences this time. Taking a closer look at the eigenvalues, we see now we're multiplying all this by 100 now. So we see that the eigenvalues are showing up. Two of them are real, or at least primarily real. Here and here, we get 218, negative 218 as a real eigenvalue. And then this last eigenvalue is negative 0.4, okay? Looks again to be completely real. These look to be completely imaginary. This pair here looks to be completely imaginary. However, we've only printed out 4 decimal places here. So in fact, it is slightly, there's a small real part here that's not negligible. Negligible would be 10 to the minus 14 or something like that. The real part here isn't completely negligible, but it's still very small. We can see that one of the second order systems is now overdamped. So we went from having 2 underdamped, actually undamped subsystems to having one that's not only underdamped but completely overdamped. All right, now we've got one that's overdamped, and now the other one. So one went from being undamped to overdamped. The other one is still underdamped. Okay. But it's barely damped. There's a little bit of damping in it. It's not undamped, and you can check out what the actual value is of the real part if you'd like. If you wanted to do it here, you would just do the real part of the say. You could take either the 1 1 or the 2 2, or pardon, the 2 2 or the 3 3. Thinking about Python here, say 2 2. The real part of that would give you some small negative number, but not negligibly small. So let's compute the natural frequency of the remaining vibratory mode, which is showing up in the 2 2 and 3 3 portion. So we take the absolute value of the second eigenvalue, gives us 2.7384. Now, you might ask for a justification. Why did I decide that the absolute value was the correct computation there? This is a complex number, right? We have the complex plane. We have some real part and some imaginary part. And what I'm saying is that this line drawn from the origin to that complex number is the natural frequency. Now, we're going to become familiar with this later on, but it's easy to justify this if you go back up to the equation we looked at earlier, and I'll just rewrite it. The second order pair was negative zeta omega n plus or minus j for an underdamped system, omega n square root of 1 minus zeta squared. So let's factor out omega n, and we get omega n times negative zeta plus or minus j square root of 1 minus zeta squared. This is a unit vector. What's inside here is a unit vector, if you will, or a length 1 magnitude complex number. Okay, so if you take the magnitude of this complex number, you get the square root of zeta squared plus the square root of 1 minus zeta squared. That whole quantity squared, you might be able to see it in your head, or you can scratch paper it, that the magnitude becomes 1. So the magnitude of this is 1, which means that if you scale it by omega n, the length is just omega n, so the magnitude is omega n. So you can just take the magnitude or absolute value of that complex number, and that gives you a natural frequency associated with it. I didn't go through that argument before because it was purely imaginary and we didn't need it. But in this case, we need this little argument here. So it would be a nice little exercise for you to prove that in a little more rigor than the hand waving that I'm doing now. But suffice it to say that you'll see that the natural frequency is just the absolute value of the eigenvalue. Here we go, 2.738. So that one survives, that mode survived. The mode corresponding to that 2.7 approximately radians per second natural frequency survived that damping that we added in. So the effect of damping was to eliminate the 10 radian per second mode and leave us with a slightly modified version of the 2.7 radian per second mode. Okay, because now it's slightly underdamped instead of being undamped, but it's still oscillating at about the same frequency. So free response now. All right, so we're going to do the same process of finding the free response of this system that's now modified with that damping coefficient. So we compute the primed phi. Again, it looks similar, but now instead of having pairs of imaginary exponentials, we have one real exponential showing up in the first one, a real exponential showing up in the last slot, and then we've got these complex conjugate pairs showing up with, so here's the real part that we weren't seeing before showing up, and it's significant. I mean, it's within a factor of 200 of the imaginary part, so it's significant enough. So we've got, so this is our phi prime. Transform, again, using the m phi prime m inverse transformation to get us phi, the state transition matrix, in the original state space basis. So our symbolic solution is to multiply the initial conditions by this matrix as we did earlier. We use the same initial condition, and we just compute it up. And again, so this is a little messy to look at, so I didn't print it out. We'll do a symbolic to numeric conversion with this MATLAB function, just as we did before. We'll plot it over the same time range, and we use the same sort of plotting routine that we did before. And this is what we get coming out. So interesting things. Right away, we see that what dominates here is a single sinusoidal oscillation instead of any sort of addition of sinusoids happening. So that's to be expected, because we don't have two modes of vibration anymore. We just have one. So that's interesting to see. Also interesting is that x1 and x2, I guess, they both have this really quick, and it looks like even x3, I think I have to zoom in here. Yeah, even x3, they have these really, really fast responses that occur in a short amount of time. If we wanted to look into that a little closer, what we would do is we would go back and plot this over, say, 0 to 0.1 seconds or something, and see that there is a very fast decay happening in this problem. And why is that? Where's that coming from? It's coming from, if we go way up here, this exponential. It's got a huge exponent on it. So it's going to decay very, very quickly. So to capture that in the plot, we have to plot that over a very short amount of time to really catch it, right? It's going to be over quickly. And so what we're really seeing in this plot is everything else unfolding, and just a couple data points are left over from that really fast decay. And once that component of the response is gone, however it enters into x1, x2, x3, and x4, it disappears in the first few data points of this plot. And everything else is dominated by that complex conjugate pair. All of these are oscillating except for x2, which after it comes up here, it doesn't seem to oscillate. It just seems to decay very, very slowly from a small number. It is possible that it's oscillating, but it does not appear to be oscillating at this frequency, and we would expect it to be at that frequency because there's only one natural frequency left in this system. So that is what we're seeing there is mainly the effect of that e to the negative 0.4 t component is dominating that one. It's a slow decay, right? It's a very slow decay. And if we were to really look closely, another slow decay is actually happening on these oscillatory components as well. Those oscillatory components have an envelope dominated by the real part of that complex conjugate pair that was left. So we go back up and look again. We see that that real part was negative 0.0015. So that is very slow. It's even slower than this negative 0.4 t, the real decay that we're seeing show up. So this part, the oscillatory decay, is very, very slow. So going back to our plot, what we've got here is a decay happening, and if I draw a straight line, you might even be able to see from one hump to the next that there's a little bit of decay. Well, it's a decay only a mother could love. I love this example. It's a lot of fun. Hope you enjoyed it. That's all I've got for you on this example problem. So tune in next time. Take care.